Hello everyone, I'm Saurab. Today I'm going to be presenting our work on adaptive duplicate suppression for multicasting and multi-access endian network. So in multi-access network, multiple nodes may send the same interest and request for the same data. And also multiple nodes may respond with the same data packet. So in current endian design, it lacks a duplicate suppression mechanism. So this will lead to a significant network congestion. The goal of this project is to reduce the number of redundant requests and data replies, and also to increase the overall bandwidth in a single hop scenario. Ideally, the suppression should be adaptive to the network conditions, which means if the network is lossless, then you would expect one interest and one data for same name by all the nodes. If it is lossy environment, then allowing a few duplicates is fine. So we categorize the suppression logic into two high-level design. The first one is look behind case. In look behind case, we record all the interest and data, the name of the duplicate count, received from or sent to the multicast phase into a measurement table. So each interest entry in this table has a certain associated lifetime. If the interest is satisfied or timeout, we remove the interest from the table. So now, before sending an interest to a data packet to a multicast phase, a node will check if it is already exists in this measurement table. If it exists, you drop the interest to data. If not, we'll go to the look ahead case. So in look ahead case, which is when you don't have any record in the measurement table, before forwarding an interest and data to a multicast phase, we wait for some time, node will wait for some time, that is a suppression time. And during this wait, if another interest or data is heard, then we cancel the forwarding. The suppression time, which is the wait time, should be adaptive, which means, if there's a duplicate is high, you increase the suppression time, otherwise you decrease the suppression time. Similarly, for the lossy links, the suppression timer can be smaller because you want to forward a few duplicates. So we use that duplicate count we compute in the previous slides to compute the suppression time, to adaptively compute the suppression time. So the main goal of this adaptive suppression time is to maintain the duplicate count for a certain name below the duplicate threshold. So this duplicate threshold is configured based on the loss rate of the environment and the network conditions. So the whole algorithm runs into 3 phases. In the first phase, if the duplicate count is above this duplicate threshold and increasing, which is here, you can see, then we exponentially increase the suppression time. Similarly, if the duplicate count is above and decreasing or constant, but it is above, then you go to phase 2, which you do nothing, which means the suppression timer does not change from the previous one. And in the third phase, if the duplicate count is below the threshold and is kind of decreasing, then you would linearly decrease the suppression time. So we compute the EWMA of the duplicate count, which is exponential weighted moving average of the duplicate, and this is computed by each node. So in our future work, we plan to do more experiments, tune the constants, and also look into the possibility of using machine learning to determine the adaptive suppression time and also to tune the constant. Thank you.
Thank you for watching this short video. My name is Kenji Kanai from the Waseda Research Institute for Science and Engineering, the Waseda University, Japan. So this video briefly introduces our work entitled Information-Centric Service Mesh for Autonomous In-Network Computing. Now, I will start the presentation. Here is an introduction. As you know, an autonomous network will be one of indispensable capabilities for beyond 5G and 6G. To realize this autonomy, container-based virtualization is a very powerful technology, and container orchestration, like Kubernetes, offers self-X capabilities, such as self-monitor, self-healing, and self-scale, etc. To support autonomous in-network computing and network-wide distributed computing, it is mandatory to shift from the connectivity-based networking to service or information-centric networking. Thus, we propose the information-centric service mesh. In the ICN world, this approach is also known as ICN-based service function chaining. So we reuse the previous research efforts and redesign the ICN service function chaining as an information-centric service mesh that supports data flows branch and merge for in-network parallel data processing. So this slide shows one of implementation example for information-centric service mesh we call the chain handler. The chain handler bridges ICN router and service function and facilitates ICN-based in-net parallel computing. We design the chain handler by adopting an ambassador container style. And also we newly implement the 6 function blocks listed in the right bottom of this slide. For proof of concept, we implement the information service-centric mesh by using CEFO and CEFPICO, one of software implementation of the CCNX developed by the NICT Japan. So left figure shows the service function chain models we test, and the right figure shows the results of the average end-to-end delay for 6 different chain models. So we test this service chain. We deploy all nodes on our Kubernetes installed in your university. From the results, we conclude that these results are very reasonable and the information-centric service mesh works properly. That's all. Thank you very much for watching this video.
Hi, I'm Mikiya Yoshida, a student of the University of Kitakyushu, Japan. Our research focuses on dynamic clustering to efficiently retrieve contents by controlling cache distribution range based on contents popularity in ICN. As you know, ICN promises efficient content delivery with in-network caching, but the performance in terms of delivery delay depends on the cache distribution range. As one approach to controlling the cache distribution range, clustering schemes using hash routing have been proposed. They have these trade-offs between the cache distribution range, that is cluster size and delivery latency. So, the cluster size should be controlled to distribute the main popular contents into each cluster. Namely, a smaller cluster size can reduce delivery delays, but if too small, the contents cannot retrieve from the cluster. It will increase delivery latency. Therefore, we propose a dynamic clustering scheme to control cluster size according to changes in contents popularity. To estimate adequate cluster size, we focus on the frequency of cache updates in a cluster. High frequency means the cluster size is too small, because caches in the cluster are updated by incoming data from outside the cluster. On the other hand, low frequency means the cluster size can be decreased, because requested contents have been retrieved inside the cluster. Now, let me briefly explain the operation of the proposed scheme. To distribute caches in a cluster, our scheme forms a cluster like this, and performs hash routing like caching separately in each cluster. Next, to adjust the cluster size, the total number of cache updates in a cluster is calculated by the controller located in it. When the calculated value x is the upper threshold, the cluster size increases, while when x is the lower threshold, it decreases. Now, let's take a look at the simulation result. We evaluated our scheme in this grid environment, where contents popularity GIF alpha varied as shown in this figure. And the cluster size varies from 2 by 2 squares to 12 by 12. As we can see, dynamic scheme improves the delivery latency and maintains a high cache hit rate, because it can adjust the cluster size to an adequate value according to condition changes. Consequently, the proposed scheme improves the delivery latency in an environment where contents popularity changes. Thank you.
Hello everybody, I'm Guilherme presenting NDN for AVC, a framework for simulations of realistic VANET applications over the NDN architecture. Vehicular network is mainly characterized by high node mobility with constant topology chains and intermittent connections. NDN is a clean slate architecture that can effectively solve many problems caused by conventional Internet architecture. NDN focuses on information rather than location, and NDN natively supports naming, data security, caching, multicasting, multi-home mobility, and naturally avoid routing loop. Suitable environments for evaluator proposal in VNDN can make several scenarios and applications feasible. There are works in the literature that do not use suitable environments for testing some vehicular proposals. Relevant information about vehicles' mobility on infrastructure is also needed. For example, road path, alternative routes, origin, destination, max speed alarm, estimate travel time, road occupancy, and so on. The influence of vehicular network on road traffic can be modeled, and complex interaction between both domains examined. Other works implement only part of the end-to-end architecture to validate proposals in a very specific vehicular network environment. They do not investigate all the properties and possibilities of the architecture. End-to-end for AVC used two popular simulators in the literature for VANET simulation, the network simulation NS3 with the end-to-end sim model, and Sumo, a simulator for urban mobility. End-to-end for AVC allows real-time bidirectional communication between Summon and NS3 to support more data about road traffic and vehicular mobility. This way, the influence of vehicular networks on road traffic can be modeled and complex interactions between both domains examined. End-to-end for AVC is the only environment to put together the benefits of the VANET network simulators and the built-in properties of the end-to-end architecture. You can also see the framework repository on YouTube, a demonstration of a use case based on vehicular traffic guidance in VANET. The main contributions of this work are highlight the need for a more realistic VANET simulation with more real-time data from the whole vehicular environment to assist different vehicular applications and also be used to improve protocols in end-to-end Layer 3. End-to-end for AVC code also demonstrates how to simulate quickly classical vehicular applications use different end-to-end properties. So, this is our poster, and you will have a little bit more details.
Hello everyone, I'm Utra Amlavani, a PhD student from Bosch and Technical University of Munich. Today I'm presenting a poster on the need for quality of service in ICN and initial direction towards resource reservation in ICN. Most of the safety critical and latency aware applications often demand dedicated bandwidth and guaranteed latencies from the network. One such application is a teleoperated driving with strong dependencies on the network. If the command from remote operator reaches the vehicle after a delay, it could already lead to a crash. The current state of ICN architectures like NDN predominantly offers best effort service. For ICN to see a widespread adoption, there is a need for better than best effort service. Quality of service is often seen as managed unfairness, where the needs of some applications are met by overlooking the needs of others. The three essential components for establishing QoS are flow specification, which defines the requirements or the desired network behavior in handling the flow classification, which is intended in identifying the right flows that need to be handled differently, and flow treatments, which are the measures taken by the forwarder to deliver the promised performance. In order to provide better than best effort service in ICN, these components need to be defined and designed efficiently. Resource reservation is one of the means to achieving QoS. In IP networks, the RSVP protocol is used to offer fine-grained per-flow resource allocation. The end user requesting resources sends an RESV packet. If the on-path forwarders are able to meet the demands, they forward the packet upstream towards the producer, else they send a negative acknowledgement back to the consumer. There are quite some similarities between RSVP and ICN. Both of them are receiver-driven. Both support aggregation of interests, multicasting, hop-by-hop decision-making, providing acknowledgements, and so on. While RSVP transmits RESV packets periodically to ensure the resource allocation is active, with ICN it can be linked to the interest lifetime. However, there are some challenges in adopting RSVP for ICN. It may not scale efficiently with state stored on a per topic, per interest, per consumer at the on-path forwarders. Expressive flow classification and specification leads to distinguished flow treatments, which challenges the quick processing of fine-grained yet varied control messages. Providing end-to-end dedicated resources is difficult with hop-by-hop producer-agnostic forwarding. Reservation of resources is targeted for the data instead of consumers. Most solutions today do not address admission control mechanism for consumers. There is also a need for a strategy to identify and mitigate wasteful reservation of resources by spurious consumers. We propose introducing traffic aggregation methods for ICN like diffserv, for instance, deploying different traffic classes for different caching behaviors. In-band reservation protocol can make use of these traffic class specification in the interest packet to make assumptions on the data characteristics and take advanced actions. Traffic classes from 5G network slicing could be a worthwhile inspiration on defining such traffic classes. There is also a need for path sharing mechanisms in ICN for providing end-to-end resource reservation. In order to optimize wasteful allocation and to avoid spurious consumers from blocking valuable resources by continuously broadcasting interest messages, one could employ an SDN-like centralized entity for the purpose of housekeeping and anomaly detection. Thank you.
Hello everyone, I am Varun and I'm going to be presenting our work at UCL on scaling state vector sync. So the SVS scaling issue comes from the fact that SVS encodes the entire state in every sync interest. While this is good for performance, it also means that the sync interest size grows linearly with the number of producers in the sync group. This creates a problem for SVS in terms of scaling, since the sync interest will exceed the MTU size at some point as the number of producers grows. It also means that SVS might have higher overhead in general in terms of the sync interest size because it is carrying information that might be redundant and not necessary at all times inside the sync group. To fix this issue, we create this notion of a partial state vector. SVS carries raw state and it carries the entire state in every sync interest. Instead of that, we carry only a partial raw state inside every sync interest. And by that, we can carry only the most useful part inside every sync interest. Note here that each piece that we create when we chop up the sync interest into smaller pieces makes sense individually to the receiver of this piece of the sync interest. This changes the question of scaling state vector sync to creating the best partial state vector using some strategy that we use for creating the sync interest. So we explored a few strategies for this. Comparing it with the baseline, the first simple one is to use a segmented sync interest where we send the entire state vector every time but in multiple packets. Then we can also try sending only the producers that were most recently active, sending a random subset of the producers, or a mix of these two strategies as we did in the random recent strategy. Of course, there are other possibilities that we need to explore, and this is a part of our future work. So we compared these strategies for scaling, creating these partial state vectors inside a simulated environment with NDN Sim, running an 8x8 grid topology with 50% loss rate on each link, and we created this artificial 30% MTU. So the state vector size in the partial state vector strategies is limited to 30% of the entire state vector size. We vary the number of fast producers, that is producers producing data every 100 milliseconds, and reduce the number of slow producers, that is producing every 1 second. On the left-hand side, you can see that the sync latency for the recent and the random recent strategies remains very low. It's in fact even lower than the baseline SVS. On the right-hand side, we can see that the network overhead, it remains low for all three partial state vector strategies compared to baseline SVS, indicating that it enables better scalability. These results together indicate that using partial state vectors is a promising direction for scaling state vector sync, and so it needs further work for getting better strategies and more investigation on how this works. Thank you.
I'm Kazuaki Ueda from KDDI Research. I'll present my research on the new bootstrapping architecture to achieve the smooth deployment of NDN. In order to achieve incremental deployment of NDN, overlay-based deployment is a promising direction. This is because it can coexist with current internet infrastructure. In an overlay-based NDN deployment, consumer creates an overlay face to the NDN router. Therefore, an IP address of the closest NDN router is required. Such IP address can be obtained during the bootstrapping. Current bootstrapping can cover two deployment scenarios. First, if access network supports NDN, IP address of internal router can be provided by the internal service, like DNS. Second, even if access network does not support NDN, IP address of public NDN hub is provided by the external service, like NDN find closest hub server. However, there are two problems. First, When access network deploys many end-to-end routers, it is difficult to determine the closest and best end router among them. Second case is the deployment at on-path transit provider. Even if the transit provider deploys an end-to-end router, consumer cannot connect to this router unless the transit provider advertises their internal router's information to the external services. So the fundamental problem is that even though end-to-end communication does not depend on the locator, the overlay-based deployment is highly dependent on the locator of the router. In order to provide consistent access to the overlay end-to-end network, regardless of the deployment scenario, we designed the new bootstrapping architecture, which uses in-network interaction and anchor IP address. Our design is as follows. First, we do not assume a destination IP address of interest as a locator of the closest end-to-end router, but we use the IP address as a locator of the anchor point, which only guarantees the reachability to the end-to-end network. Next, we introduce the in-network interaction function, which routes the incoming interest to the closest end-to-end router. By delegating the discovery of the closest router to the in-network interaction function, our bootstrapping architecture can provide consistent access to the end-to-end network in all deployment scenarios. Thank you for listening.
Hello everyone, I am Prayash Porter and today I will be presenting our work on improving versatility of VERSIC trust schema. VERSIC is the promising next step to establish the trust relationships among different entities and automate the overall signing and validation process in a very user-friendly way. In VERSIC, the trust relations are described using a declarative language which later compiled to a complex binary format, and consumers and producers use the signed binary format to sign and validate data packets. Although the goal of VERSIC is to facilitate versatile security, the initial design assumptions mainly focused on local environment like IoT. However, we want to use VERSIC in more generalized environments and analyze whether the current binary encoding can achieve it as it is or not. Based on our analysis, we identified several ways to make VERSIC more versatile. In VERSIC, a user can define all the certificate chains possible in a system, and theoretically there is no bound on the number of chains. However, in the binary, a bitmap of size just 1 byte is used to represent it, which limits the total number of certificate chains to only 8. For a smaller environment, 8 chains might be sufficient, but for a large Indian application, we might need more than 8 chains. This is merely an encoding issue that can be solved by using a different data structure like vector. VERSIC binary uses a token table, which keeps all the words or tokens used in a schema so that later the token index can be used instead of the whole word. However, due to the token table size, only 128 unique words can be used in a schema. Again, for a small schema, 128 words might seem sufficient, which might not be true for a large schema. This can be solved by using endian names directly. One of the assumptions of VERSIC is that one publication will have multiple variants, and to group similar type of publications and compress them effectively, VERSIC introduces several mechanisms. However, in a few pilot applications we have explored so far, like NLSR, ChronoChat, etc., we have found that the publication can be diverse, and these additional mechanisms to create actually overheads instead of saving space. We have a few more insights that you can find on the poster. So based on our findings, we have designed and developed a new binary format where we have used endian names directly to overcome the issues mentioned before. In some cases, for example, a schema with more repetitive words or a schema with multiple variants of a single publication, the size of the updated binary can be larger than the VERSIC binary. However, we can use any compression method like JZip if size is much a concern. Here we can see the estimated comparison. Although VERSIC performs better than our proposed no compression method, JZip can reduce the size in a great extent. So visit our poster and it will have a bit more technical details than the 3-minute talk. Thank you.
Hello everyone, my name is Ten Liang. Today I'm going to introduce our work, low latency internet live streaming in named data networking. What's the biggest obstacle to ICN and endian deployment? Probably lacking of application support. One solution is to endianalizing applications, which means to translate between existing application-level protocols and the NDN. In 2018, we translated IMAP and NDN, XMPP and NDN for email applications and instant chat applications. In 2020, Chavoosh translated Dash and NDN for on-demand video streaming. This year, we translated HLS and NDN for live streaming over NDN. This work is on top of the latest work. What is low latency HLS and why we choose it? HLS and also Dash, they are a receiver-driven protocol to achieve adaptive bitrate video streaming, and low latency was not a primary goal. This year, Apple added low latency HLS with 5 extensions on top of HLS to achieve low latency. So how do they work? They periodically pull playlists, and then you know what's new video chunks you retrieved. We're interested in it because NDN is also a receiver-driven model. They can help to design low latency data retrieval in NDN. So to NDNize the 5 extensions, 3 of them are communication related. They use the term block playlist preloads, which means to hold on requests until the expected playlist is generated. The second one means to hold on requests until the expected video chunks are generated. The third one is to provide delta updates instead of the whole playlist update. To NDNize them, first, they need to add a condition to requests, and in NDN, we have these interest parameters. In extension 1 and 3, we need. They also have on-demand data generation with extra logics. Also, you have to hold on request interest until data is generated. This is the biggest lesson we learned because data can be transmitted immediately back to achieve low latency. There are 2 other application-specific extensions. One is smaller video chunks. The other one is more information in the playlist. We don't need special support for them. In the evaluation, on the right side, we have a video publisher push the stream into a server, which transcoded into LLHLS. We have a module to convert it into NDN to serving over NDN. On the left side, we have a Shaka player, which from Google, we have a communication module to translate LLHLS into NDN. So the video size from 4-second HLS into 0.5 low latency HLS, we have buffer size 3 video segments as the default. So latency from 27 seconds into 3.5 seconds. Thank you for listening.
Hi, I'm here to present our poster named Intertrust Establishing Interzone Trust Relations. In NDN deployment, a trust zone may process data packets from other zones. For example, mGuard and testbed all own their trust zones, but testbed's routers should verify the perfect announcements signed by mGuard certificates. Look at this figure. Testbed and mGuard have their trust anchors and corresponding verification chains. Testbed requires 2 functions if it wants to consume data packets from mGuard. The first one is how to authenticate the trust anchor in mGuard. We call it zone authentication. The second one is how to define the security rules about the verification of mGuard's data. We call it zone authorization. Our work is to build a bridge between 2 trust zones. In general, we suppose that an entity EA in a trust zone ZA wants to consume a data packet produced in ZB. In zone authentication, the controller of ZA will issue a certificate TB code whose public key is the same as the trust anchor TB. This certificate will be signed by the trust anchor TA. We call TB code the proof of zone recognition POR. There exists a naming convention between TB and TB code so that entities in ZA can get POR's name by using TB's name. In zone authorization, the controller of ZA will provide security rules to the entities in ZA. It will obtain ZB's internal naming convention and define the security rules on the data produced by ZB. After that, it will get a new trust schema. Then it will install the latest trust schema on all CA's entities to finish the zone authorization. When the entity wants to verify the data, it can follow the verification chain in ZB to the trust anchor TB first. Then it can use the naming convention to get the POR TB code to continue the verification procedure in CA. From the above discussion, we learned that a trust zone will not only exchange data packets within itself. Our work is to build a bridge between trust zones. We also want to know that in the trust, the consumer zone unilaterally authenticates the producer zone. It doesn't have to be bidirectional so that it will be more flexible. Thank you.
Hello everyone, my name is Italo from Federal University of Bahia. I'm going to be presenting the poster on supporting forwarding strategies and sync protocols through end-to-end distance vector routing. As we know, routing, forwarding strategies, and sync protocols are three well-known components of the end-to-end, and it is important to understand how they can help each other, how they can benefit from each other. For instance, in the absence of routing, some forwarding strategies try to discover which data is available by broadcasting a subset of interest. And we also know flooding in ad hoc scenarios can impact the wireless performance. The same way, the sync protocol without routing has to be extended to also figure out which data is reachable. In order to understand the relationship between sync and routing, we have a study case using NDVR and SVS. NDVR is a end-to-end distance vector routing protocol, is a lightweight routing protocol. SVS is a well-established synchronization protocol based on state vector. And DVR exchanges a few interests in the network to discover the neighborhood, and as soon as some router announces a new name prefix, we request the distance vector information, validate that information, and learn the new reachability information. The experiments that we executed take into consideration different factors. So one of them is the strategy. So we use NDVR plus SVS. We use SVS alone. Another factor is the number of nodes. So we work with 20 and 40 nodes. All the nodes are producer and consumer. And we use reference point group mobility. For data generation model, we use low volume and high volume, and the metrics are based on the output. Those are the results. We can see that in the low volume scenario, the results are pretty much the same. Even though the SVS alone has a bit of better performance because of the overhead of the protocol. When we look at the high volume scenarios, we see that actually the routing protocol helps a lot the synchronization because we have much better good put. For instance, for 40 nodes, we have 15% of better good put. The same thing for routing and forwarding strategy. When we use the routing protocol supporting the strategy, no matter if it's multicast. In this case, we also compare using ASF for mobile nodes. The routing protocol actually helps. So in this poster, we presented the comparison between using routing protocol to support forwarding strategies and sync protocols. And we see that when we have a lightweight routing protocol, the forwarding strategy can only do its job of selecting the best face over multiple faces whenever data is reachable. Also, the sync protocol can benefit from the routing because we only send the synchronization when members are reachable. For future work, we want to evaluate new experiments, new metrics, and also evaluate different forwarding strategies with sync in routing protocols. Thank you for your attention.
I'm Ryo Nakasuji, a master's course student at Osaka University. I'd like to talk about our poster on cache-aware dynamic adaptive streaming over information-centric networking. We discussed DAS over ICN. ICN brings benefit to DAS, specifically in network caching can reduce the network traffic. However, it causes several challenges. For example, it introduces multiple control loops and intermittent cache hits. These factors give negative effects for DAS, such as bitrate fluctuation and rebuffering. Therefore, the objective of this poster is to investigate how cache awareness contributes to the challenges. To achieve this objective, we preliminarily design a simple cache-aware DAS algorithm. CAD algorithm consists of two important parts. CAD estimates the bottleneck bandwidth using segments served from the server, so CAD estimates bandwidth between client and server. In addition, CAD selects bit rate considering a risk of future cache misses. It increases bit rate when it can download the next n segments of the selected bit rate, even in the case of cache misses. We simulated this algorithm. Please look at Figure 1. The conditions of our experiment are simple. Then, we compare a buffer-based approach, CAD1 and CAD2. CAD can suppress the bitrate fluctuation and rebuffering because CAD can identify cache hits or misses. Moreover, CAD can more suppress the fluctuation by considering the cache miss risk. Finally, our next challenge is how to infer cache hits or misses. Thank you for listening.
Hello everyone, my name is Luo. This presentation is about a global name mapping system for ICN IP coexistence. Given the high costs of reconstructing the current internet, ICN IP coexistence becomes a feasible solution to achieve the benefits of ICN without changing the entire internet. And name mapping services are required in many ICN IP coexistence architectures. For example, dual stack gateways want to find each other, overlay schemes need to locate the nodes, and the consumers want to retrieve content globally. To meet these requirements, we're going to introduce a distributed system with general query interfaces, dynamic update mechanism, improved query performance, and good scalability. Let's start with the architecture. It consists of 4 types of entities. Name client is a client library that provides general query interfaces, the core of the system. The name servers compose an overlay network and reply the incoming queries, and the update proxy and prefix administrator are responsible for managing the dynamic updates. A typical working scenario is shown in the right figure. Data retrieval is based on intra-data communication inside the ICN edges, while the traffic among the dual stack gateways goes through the IP backbone. The edge gateway acts as a name client to obtain the target gateway address from the name servers, and the ICN nodes along the path can achieve the benefits of the ICN cache. We define the query message format that is compatible with standard DNS messages. In this example, the query carries a name with a specific search range, and the answer from the server carries the actual levels of the matched prefix. To enable the system to adopt different processing strategies according to the queried prefix, we design a routing module for the name server. The routing module adopts the longest prefix match in the row set for each query, and the row set can be either manually configured or dynamically updated. For improving the query performance, we propose a novel cache scheme called prefix expansion cache. Its lookup, insert, and delete operations are of constant time complexity. It expands the query and associates them with the corresponding answer. Its cache rate is improved because more query patterns are satisfied. Moreover, we introduce hierarchical authorization. Prefix authorization is performed by issuing certificates. As a result, a global trust tree is formed, and the certificates should be verified during the dynamic updates. We implemented this system, and the preliminary evaluation results show that the system outperforms legacy DNS for query performance with cache enabled. Even if we disable the cache, the query performance is still of the same magnitude as byte 9 and is insensitive to the row set size. And we are going to take more comprehensive evaluations and further improvement in our future work.